Today I will discuss nature of things. Suppose this marker, I'm dropping it. Where does it go? It goes down because of its tendency. So if this marker has tendency to go down to the earth when I leave it over here in the atmosphere, same goes for the zinc strip when it is dipped in the solution of its ions. Suppose I had a zinc strip and I were to dip it in the solution of its ion. It would have a tendency to lose its electron on the strip and become zinc ion. Okay, and now if I were to look at a copper strip, what would it do? The ions from the solution here would convert into copper atom and take up electrons. So both of these are showing reverse tendencies. One is converting from zinc into Zn plus 2 and leaving its electrons. The other is taking up electrons. Copper plus 2 is taking electrons and converting into copper atom. So what are these tendencies of nature called? This tendency of nature is called oxidation. And this tendency of nature is called reduction. Now we will talk about these in detail, oxidation, reduction. But first, let me tell you, I'm Shahab Ahmad and this channel is called Defying Mediocrity. And today's chapter is Electrochemistry, in which we study the interconversion of electrical and chemical energies. This is not anything normal to see that element showing their tendencies for the electrons. Toward the electrons, one will push them away, the other will attract them, and because of them we can use these tendencies like we use potential energy to do some work, like potential stored in different kinds of things. Here again, this potential of different elements to repel or attract electrons, we can use it to run machine to do some work as we do with the batteries. We are lighting our bulbs with it, we are running our fan with it. So this tendency of elements is very phenomenal. So now to oxidation. Oxidation, as we could see over here, it is the increase in some number. I am increasing this number, which is written on zinc 0 goes to zinc plus 2. So means some number has been increased. And to this number I called oxidation number. Oxidation number. So oxidation number is the apparent charge on an atom or ion. Okay, so it is the apparent charge here on this atom. It is 0. Why is it 0? Zinc over here is a strip. When I take it a pure metal, it has 0 oxidation state. But now when it has lost its electrons, it now reads plus 2. Now it has the oxidation state of plus 2. So oxidation number or oxidation state is the apparent charge on an element, on an atom, on an ion. Okay, but here we learned that when an element is in its natural state, here it is in its natural state because zinc has all other zinc atoms surrounding it. So the metallic zinc has 0 charge. Means when an element is present in its natural state, like zinc metal, sodium metal, copper metal, all surrounded, these atoms are all surrounded by the same of its kinds. So here their oxidation state would be 0. Oxidation number, their oxidation state would be 0. Now again, if I had oxygen, suppose, surrounded by, or are bonded to another oxygen, or nitrogen bonded to another of its kind, or sulfur in S8 form, or phosphorus in P4 form, or hydrogen in H2 form. Here we see that the electrons in these cases are distributed equally. Now, none of the atoms is attracted the electron more toward its side, so it is equally distributed between the two. So these atoms in all these cases, as a whole, these molecules, these elemental molecule, this is a homoatomic molecule or homoatomic molecules, they have zero oxidation state. Okay, now take a molecule like argon or xenon. They too have zero oxidation state because we see that it's commonsensical that number of protons and electrons are equal. So charges are equal means zero charge is a whole on them. So now we learned that elements, if we find them in uh, monoatomic form, monoatomic molecules, or diatomic molecules, or multiatomic molecules, polyatomic molecules, or metallic elements, when there is nothing attached to them, we'll find them in zero oxidation state. Okay. Now, I am finding hydrogen over here in zero oxidation state. But what happens when hydrogen is not attached to one of its kind, when it is attached to something else? You will find hydrogen in two distinct oxidation states then, and it is not bonded to one of its kinds. Okay, one -1, the other +1. Okay, so hydrogen shows here. I will talk about hydrogen. Okay, bending into a metal, it will show -1 oxidation state in metal hydride. Suppose M represent a metal and H represents hydrogen. So as metal is more electropositive, so metal will show positive oxidation state and hydrogen will show negative oxidation state. I will give you example. Sodium hydride, sodium +1, hydrogen -1. Magnesium hydride, MgH2, magnesium +2, hydrogen, 2 hydrogens -2, 1 hydrogen -1. Okay, so means hydrogen in metal hydrides shows -1 oxidation state. But with non-metals, you will find it in +1 oxidation state. Okay, +1 with non-metals like NH3, like HF, okay, like HBr, like HCl, etc. Okay, here you can see nitrogen with more electronegativity pushes the electron, pulls the electron toward itself. So this becomes negatively charged and our hydrogen becomes positively charged. Okay, so nitrogen -3 and 3 hydrogens +3, 1 hydrogen +1. Okay, fluorine with -1 and hydrogen +1. So this was about hydrogen. What about oxygen? Oxygen shows variable oxidation state too. Okay, let me take the marker oxygen. Oxygen, you will find it in all its compounds like H2O, like uh, HClO4, like H2SO4, like etc. etc. You will find it in -2 oxidation state. Okay, but just in few things you must remember them, that in few compounds oxygen shows different oxidation states, and we will talk about it. The first one, I will talk about peroxides. In peroxides, oxygen show -1 oxidation state. Should I give you an example? Oh, be ready. Na2O2. We will talk about its preparation. How is it prepared? How is it formed? When we talk about inorganic chemistry, in inorganic chemistry, we'll talk about the formation of this oxide in detail. Okay, another one you must have known it. H2O2, hydrogen peroxide, strontium peroxide, barium peroxide. Okay, so here oxygen is in -1 oxidation state. Another thing in which oxygen is in different oxidation state than -2, that is not peroxide but superoxide. In superoxide, it is in -1 or 2. Superoxide. Should I give you example? Yes, I must. Okay, that is francium superoxide, Fr. I must write. Okay, potassium superoxide. Okay, cesium superoxide, CS. So here, oxygen is in what oxidation state? It is in -1 or 2. Okay, so this was about hydrogen, oxygen elements. But now you must remember that in our periodic table, we must remember 14 elements that have fixed oxidation states, and remembering them will give us a lot of knowledge about finding oxidation states of different elements in a compound. Okay, those 14 elements are: number one, group 1a elements except hydrogen. So you will be left with lithium, sodium, potassium, rubidium, cesium, and francium. Okay, are these are just six. What are other add elements? Other add are group 2 elements, six group 2 elements: beryllium, magnesium, calcium, strontium, barium, and radium. And what are the other two elements? Now they become 12. What are the other two elements? Because we said that there are 14 elements that show fixed oxidation state. Other two are, one is fluorine and the other is aluminum. Okay, so now tell me, what are their fixed oxidation states? So this group will always show +1 oxidation state. You will find them in all their compounds. These elements will show +1 oxidation state. Okay, this group, they will always show +2 oxidation state. In all their compounds, you will find them in +2 oxidation state. What about fluorine? What about aluminium? Okay, fluoride will be in -1 oxidation state and aluminum will be in +3 oxidation state in all its compounds. So now we have the knowledge about oxygen, hydrogen, and these fixed oxidation states elements. Now we will be able to find the oxidation state of an element if we were asked to uh, suppose I was asked to find the oxidation state of chlorine in HClO4, because now we have fixed the oxidation state of fluorine, but chlorine no fixed oxidation state. It can show different oxidation states depending upon to which element it is attached to. Okay, now the question is to find the oxidation state of chlorine in HClO4. Okay, I will do it over here. Should I do it over here? Okay, I can give it a try. Is this part visible? Okay, so I will do it over there. I am asked to find the oxidation state of chlorine. Now, first of all, what is the oxidation state of this whole compound? This whole compound has zero oxidation state. Why? Because the number of protons and electrons are equal in this compound. So its oxidation state as a whole is zero. So we must remember its whole oxidation state is zero. So the sum of all the oxidation states of this compound will be equal to zero. So if I were to add the oxidation state of hydrogen plus the oxidation state, the oxidation number of chlorine plus the oxidation state, oxidation number of oxygen, I will find it to be equal to zero. As here I have two oxygens, so I must multiply the oxidation number of oxygen, sorry, not two, four oxygens, four oxygens. So I must multiply four with the oxidation state of oxygen. Okay, so I must add the oxidation state of all these to be equal to zero. Now I must put the oxidation states in places of the elements. So chlorine I am finding, I'll put chlorine in its place. In oxygen and hydrogen I know. What is the oxidation state of hydrogen? Instead of other than metals, it will show the oxidation state of +1. Okay, as we discussed it over here with non-metals, it is showing +1. So hydrogen +1. +1. And how many hydrogens I have? Just one hydrogen, so I must multiply 1 with +1. So 1 with +1 becomes +1. And Cl in its place, because I'm going to find oxidation state of Cl. And the oxidation state of oxygen is -2 in its compounds except oxides like peroxide or superoxide. It is neither peroxide nor superoxide. It is normal oxygen. So normally we will have it in -2. Okay, now this is +1 plus Cl. 4 into -2 becomes -8 is equal to 0. Okay, now +1 -8, you are better at math than this. Okay, so +1 -8 becomes -7. So Cl -7 is equal to 0, or Cl is equal to, if I were to add +7 to both sides, I will get Cl is equal to +7. Cl is equal to +7. So chlorine is in +7 oxidation state in HClO4. Okay. Now, a lot about the oxidation number. What about oxidation? We left it over here without discussing it. Oxidation is the increase in oxidation state. Okay, it is the increase in oxidation state. As over here, it goes from 0 to +2. Is my mic running? Yes, it is running. Okay, so the increase in oxidation number, increase, I must add the word increase over here. Now, the increase in oxidation number could be brought about by different means. One is over here is the loss of electron. Increase in oxidation number is called oxidation, and it could be brought about by removal of electron. Electron or electrons is over here, electrons to electrons. So this is case one. So removal of electron could be oxidation. Another thing, it is not the only thing to do to increase the number oxidation state of an element. We could also add up oxygen or another electron negative atom. Okay, if we were, I'll write the over there. Okay, so now talk about another thing. How can we do oxidation, increase the oxidation number by another method? That is number two, add oxygen to increase the oxidation number. How? Like, let me give you an example. Suppose I have carbon and I add up some oxygen to it. I will convert it into carbon dioxide. Now here, now you can find the oxidation state of carbon over here. Oxygen is -2. -2 into 2 becomes -4. So as a whole charge is 0. 0 carbon plus -4. So carbons become +4, because if I shift this -4 into the other side of the equation, it becomes +4. So here carbon is in +4 oxidation state. Okay, now, but what about here? Here it is in 0 oxidation state, and we discussed in the case of metals, in the case of, sorry, elements. So carbon in elemental form will have 0 oxidation state. So it goes from 0 to +4, mean an increase has happened. So increase in oxidation state is called oxidation. But by which means this has been brought up? This has been brought up by addition of oxygen. Can we do it another way? Yes, we can do it another way, by addition of another electronegative atom. Addition of another electronegative atom, like atom or element, like suppose the example coming into my mind is fluorine. When iron reacts with chlorine, suppose FeCl2. Okay, here you can see that the oxidation state of iron has gone from 0 to +2. Here chlorine is in -1 oxidation state. So chlorine goes from iron goes from 0 to +2 oxidation state. Mean oxidation state has been increased. By what means? By addition of another electronegative atom. Okay. Now, is this the whole case? Just these are the cases in which I can oxidize, with the help of which I can oxidize a substance. I can increase the oxidation number. No, there is another way. By removal of hydrogen. Like here, you can see. Suppose ammonia. I remove hydrogen from ammonia. What will I get? N2H2. Okay. Let me balance it. Okay. Now, you can see that nitrogen here was in -3. So from -3 it goes to 0. -3 to 0 is increase. So this increase in oxidation state has been brought up by removal of hydrogen. This is also oxidation. Then what is reduction? The reversal of all these. Okay. The addition of electrons is mentioned above. Addition of electrons. Okay. Or removal of oxygen. Like, suppose I had copper oxide and I removed the oxygen from copper oxide and I converted into copper atom plus zinc oxide. Okay, here you can see that oxygen has been removed. The again, I must say, here it is the increase in oxidation number. This is decrease in oxidation number. So I have decreased the oxidation number. I can prove it. Here copper is in +2 oxidation state, and now you can see copper over here is in 0 oxidation state. So from +2 to 0 is the decrease in oxidation state. So this decrease in oxidation is called reduction. Decrease in oxidation state could be brought about by addition of electrons is the here it was removal of electrons, here we add electrons to reduce something, or removal of oxygen is over here. Here we discussed the addition of oxygen, but here it is the removal of oxygen. Removal of oxygen is doing reduction. Okay. What about the addition of hydrogen? It is also reduction. Okay. Addition of hydrogen is also reduction. This is the example of it. Now, talking about oxidation reduction, it happens in pairs. You can see that oxidation reduction is happening simultaneously. Take this example. Suppose I will elaborate it over here. The example of copper oxide reacting with zinc to convert it into copper plus zinc oxide. Hey, so here we see that copper is being reduced to copper. Copper oxide is being reduced to copper. So doesn't zinc help it to be reduced? Didn't zinc act as an agent in this reduction? So zinc acted as an agent in this reduction. So we call this zinc reducing agent. Okay. So does is just this zinc? Is it about just zinc to be acting as a reducing agent? No. In different reactions, different substances act as reducing agent. Like could be sodium, they act as a strong reducing agent. Lithium, calcium, magnesium means metals, especially of group 1 and group 2, and aluminium, and we discussed zinc. So they act as reducing agents because they are ready to lose electron, to give up electron to other things, other species to which they are reacting. So they are good reducing agents. What are other reducing agents? Elements in their low oxidation state, like suppose tin is in low oxidation state over here, +2, it could be in +4 in higher oxidation state, and we will discuss that in oxidizing agent. Like iron in +2 oxidation state could be acting as reducing agent. And other thing like acids of halogens like Hi, which is stronger reducing agent than HBr, and so on and so forth for HCl and HF. So the strongest acid and the strongest reducing agent too. Now we have talked about reducing agent, but what about this species? This is acting as an oxidizing agent, as we could see that it has oxidized zinc. It has helped zinc to be oxidized. So helping in oxidation mean agent of an oxidation. As it is helping in oxidation, it is an agent of oxidation. Okay, so copper helps in oxidation, so it is oxidizing agent. Is just copper oxide, is just this an oxidizing agent? Don't we have other oxidizing agents? We have other oxidizing agents. Other oxides also act as an oxidizing agent, like SO3 or carbon dioxide or chromium oxide. So all these oxides act as an oxidizing agent. Elements here we talked about in lower oxidation state acting as a reducing agent. But elements in their higher oxidation states act is an oxidizing agent, like suppose SnCl4, FeCl3, here Sn in +4, Fe in +3, KMnO4. Okay, you can find the oxidation state of Mn over here. -8 plus 1, so -7. -7 when it turns into the other side, it becomes +7. So +7 over here for Mn. H2SO4, sulfur in +6 oxidation state. K2Cr2O7 +6 in +6, I think, in oxidation state of it. Okay. HNO3, okay, it is in what, in +5 oxidation state, nitrogen in +5. HClO4, as we discussed over there, in +7 oxidation state. So you can see these species, in these species, these central atoms are deficient. They need electrons, they are in need of electrons, so they can eat up electrons. So by eating up electrons, they are helping the other substances to be oxidized, is they are removing electrons from other substances, and removal of electron is called oxidation. So they are helping in oxidizing other substances, so they are called oxidizing agents. Now, after talking about oxidizing and reducing agent, should I mention, yes, I should mention that elements like non-metals, like here we mentioned metals, non-metals like fluorine, chlorine, nitrogen, oxygen, they act as an oxidizing agent because of what? Because they can take up electrons. And I must mention this. Fluorine is the strongest oxidizing agent, strongest oxidizing agent. Okay. And here, the strongest reducing agent is lithium. Sorry, lithium in in aqueous medium. But in dry condition, cesium is the strongest in dry condition. Okay, but there are few exceptions, like uh, hydrogen, carbon, sulfur, and phosphorus. These are reducing agent. These are non-metals but act as reducing agent. Okay, so we must remember them. There's these chaps, the hydrogen, carbon, sulfur, phosphorus. Though they are non-metals, we put them in oxidizing category because they are electronegative and they can eat up electrons. But these four are what? These four are reducing agents. Okay, now we talked about these things, oxidizing and reducing. How about finding the tendencies? Like here we can see that it can attract electrons. Uh, these can give up electrons. But what about plotting a graph, a chart of these oxidizing and reducing agents and finding their affinity, the value of their being oxidized or reduced? So there is, now here I will take this as an example. Copper is able to draw off electrons and being reduced. Okay, zinc has the ability to leave its electron in being oxidized. But how much these elements have the tendency? So for much we must measure it against some against a standard. And so to measure their oxidation and reduction potential, their ability, potential mean ability, their to measure the oxidation and reduction potential of these elements, we must compare it to a standard. And here we take the standard of hydrogen electrode. Here we take the standard of hydrogen electrode. What is standard hydrogen electrode? We represent it as She, standard hydrogen electrode. I must remove this. Okay. Here I will draw standard hydrogen electrode. In short, we call it She. A tank filled with 1 molar solution of HCl to give us H plus ion, 1 molar H plus ion. So this must be 1 molar. Okay. Having a glass tube inverted, which is constantly pushed with hydrogen with 1 atm pressure, and here we have a wire of platinum having connected with a plate of platinum that has some platinum atoms coated above it called uh, platinum black. So this metal surface, so that it could increase the surface area of the metal. So I have this platinum wire, PT wire, and this is platinum plate. Okay. So this is the construction of it. Now we saw the tendency when copper ions were put, when copper strip was put in its ions and zinc strip was put in its ions, we saw different tendencies. One was giving off electron and the other was gaining up electrons. So in one case, the ions were converting into atoms. In the other case, atoms were converted into ions. Now, here we see the equal tendency for both hydrogen gas taking up electrons and converting into hydrogen ions, and hydrogen ions taking up, yes, here I must say that if it is converted into ions, so it must give off electrons. And again, hydrogen ion taking up electrons and converting itself into hydrogen gas. So both of them have equal tendencies. And we have taken the potential of this oxidation potential plus reduction potential, both of them equal to 0. The oxidation plus reduction, here we see oxidation taking place, here we see reduction taking place. Okay, but in both cases it has 0 potential. So we have taken this 0 and we measure other potentials, the potentials of other elements against it. So we connected with other elements and their electrodes. Here I have taken zinc electrode, I have taken copper electrode. So I will connect it over here to standard hydrogen electrode and measure its potential against it and find how much. Now I can find how much capacity, how much potential this copper has to take up electrons, how much potential the zinc has to give off electrons, because there are other species that can take or give off electrons. So now we can plot, now we can measure it against standard hydrogen electrode, She, and then find out the number by how much one is different from the other. So what we do, we combine it with standard hydrogen electrode. So by combining it with standard hydrogen electrode, here we take a voltmeter, here we take the zinc electrode, now here this is zinc electrode, here this is zinc solution, 1 molar. Okay, so this whole condition, this is a setup. Okay, I have now paired both the electrodes. This half cell I have connected with this half cell, okay, and we will add them both with the help of a tube that contains an electrolyte, okay. This is a bridge, a junction, okay, which connects both the half cells, and it has an electrolyte like KNO3, suppose. A wet cotton of KNO3 could be sufficient, or a wet tissue of KNO3 would be sufficient, which you could take it. So we must have what it does. We will talk about it. It balances the ions in both the cases. Here I will see the increase in Zn plus 2, so NO3 minus will come over here, so to balance the charge. Okay, here I will see the decrease in the H plus, so K plus will come to replace it as plus ion, positive ion. Okay, here what happens? Okay, now we will see the same reaction. Zn will leave off its electrons and convert itself into Zn plus 2. Sorry. So these electrons will go in this wire. These electrons will move in this wire toward over here. And what I will see, the reaction taking place over here. So H plus will take those electrons and convert to H2 gas. Here I will see the reduction in H plus ions. So K plus from over here will move to this solution, and NO3 minus is decrease in as I will see the increase in plus charge over here. So minus will balance it over here. Okay, here I see the oxidation half cell. Oxidation half cell. Okay, here I'll see reduction. So what happens when we pair up zinc electrode with hydrogen electrode at standard conditions? Like I have taken hydrogen ions 1 molar over here in the solution. I have taken 1 atm hydrogen gas comes over here to this electrode. Okay, now I have taken 1 molar solution of zinc ions, and this whole setup is set at 298 Kelvin, means room temperature, and 1 atm pressure. So the reading taken at this now in this condition are called standard reading. So this is standard electrode potential. Standard electrode potential. So I want to find the standard electrode potential for this whole setup, for this for this reaction. So for this reaction, the standard electrode potential will be the electrode potential at oxidation half cell plus the electrode potential at reduction half cell. Standard electrode potential at reduction half cell. So I find the electrode potential over here. The my clock was reading 76 volts. So plus 76 volt was my potential, plus 0.76 volt was the reading of the clock over here. So I put it the total cell potential equal to 0.76. So it must be the oxidation potential, which I don't know, because here oxidation is happening at zinc. I don't know what is the oxidation potential of zinc. I'm trying to find it. And the reduction potential. And we talk about the reduction potential of She is 0. So plus 76 becomes the oxidation potential of zinc. So with this way, I now found out the oxidation potential of zinc, and I can with the same way find the reduction potential of copper. Here, when I join both the cells, when I combine it with She, what I will find that zinc is being reduced, and here oxidation will take place. With the same thing, with the same setup, I found out that the reduction potential, E naught reduction of copper was equal to 0.34 volts. Okay, and then by doing this for all the elements, I found out that I came up with a chart that here I plot the standard reduction potential for all the elements of periodic table, and I graphed them with increase in number. At the top of the list I had lithium, then sodium, then potash, or etc. This is not perfect, but I am giving just a hint. And then zinc, aluminium, iron, or plumbum. Then I got hydrogen, and then I got copper and aluminium, sorry, copper and uh, silver and gold, and then I got chlorine, and then at the end I got fluorine. So just to give you a sense, I combined one of them, each one of them, one by one with standard hydrogen electrode, and found out their potentials. And the reduction potential was plotted then. So I found out that the reduction potential of lithium was the lowest, So negative. These all have negative value for reduction potential. Mean they were ready to be oxidized, not reduced. And here it is 0. Here again we see positive values. So the most positive value was for fluorine, which was easy to be reduced. So here I see that these elements which are at the top of the table, they are easy to give off electrons, but at the bottom of the table I see the elements that are easy to take up electrons. So copper I am finding it beneath hydrogen because it is easy to be reduced, so I can reduce them. These elements could be reduced, and these are easy to be oxidized. So now what happens? These elements can replace, so on the basis of this table I can deduce few things. I must say few things and then we will wind this up. So the elements which are above hydrogen in the standard reduction potential chart, they can replace hydrogen. They can, when they react with the acids, they can give off hydrogen, like they can evolve hydrogen gas from the acid. Elements which are above hydrogen, when they react with acid, they can give off hydrogen gas. When they react with acid, they can give off hydrogen from the acid. Okay, another thing, these elements can, what they can do, another specialty, they can replace these elements from their salt. Suppose I had a salt of copper sulfate and I put zinc in that salt. I will find that copper is being replaced by zinc in the salt. So the elements above hydrogen can replace the element below hydrogen from their salts. Or same case, same happens with elements. One element above the other can replace it from its salts. So here, why does this happen? This is so much logical because the oxidation potential of this thing is higher than this one. So this is more likely to be oxidized. So zinc is oxidized and zinc becomes Zn plus 2 SO4 and copper becomes copper atom. So copper goes to from plus 2 to 0. Okay, so as copper has the tendency to be reduced as we saw. So this is so logical now. Now with the chart, I can also, this now becomes so interesting. From this chart, I can, is my mic turning? Yes. From this chart, I can create voltaic cells, okay, by combining any of these two elements. Suppose here the oxidation, the reduction potential of calcium is I think 2.17 or something. You correct me if I'm wrong. So 2 point something in minus means its reduction potential. It has negative reduction potential. So it must have positive oxidation potential. Okay, so this will be positive 2 point something, 2.18 or 17 in positive oxidation potential. Okay, so if I combine this calcium with with another element of its another element, suppose I combine it with copper, which has 0.34 oxidation positive reduction potential. So and the E naught of the cell would become, E naught of the cell would become, suppose I were to leave that alone. I am combining these two cells. Okay, now you will be able to find the E naught of the cell. Okay, as we saw that copper gains electrons, okay, to be converted into copper. So as zinc loses electron to be converted into zinc ion, and both have some ability, some potential, and we can use that potential, that push of it, this push of the nature, as we started our discussion with. Suppose I am using Canov rule here. Okay, so this push of the nature, we can use it to run some electricity, to light up a bulb or whatever we do. So what will be that push equal to? So E naught of the cell would be equal to E naught oxidation plus E naught reduction. And from where can I find the values of E naught? So I can find it from the chart. Here, the copper has E naught reduction of plus 0.34 and zinc has E naught reduction of minus 0.76. So its reduction is in minus. So its oxidation must be in plus. Is this reaction, if we have taken this is negative, so this must be then positive. So this value must be in positive 0.76 volt, as this is 0.76 but in negative, so this must be positive. So the oxidation potential of Zn is a 0.76. So we must add both the potentials of the half cells. Here the reduction potential is 0.34 plus 0.34, 0.34 plus 0.36. This becomes 1.10 volts. And this is the potential of the Daniell cell. This is called Daniell. Daniel, whatever the name must be, forgive me. So Daniell cell, this is the Daniell cell. Okay, and this is its potential. Then what is the cell notation for this reaction? The cell notation for this reaction is, we have taken, first of all, we must write the oxidation half of the cell. So this is the oxidation half of the cell, oxidation half of the cell, and we must oxidation half of the cell. Here what happens, zinc converts into Zn plus 2 in aqueous medium of 1 molar solution. So we must draw the slash in between the medium, the metal, the element and its ion or its medium in which it is being dipped, and double slash for the salt bridge, and then copper from plus 2 ions of its 1 molar aqueous solution converts into copper. So this is the oxidation half of the cell, and this is the reduction half of the cell. So oxidation happens at what, well, you must remember red cat. Okay, so the electrode at which reduction takes place, it is called, the electrode at which reduction takes place, it is called cathode. At cathode, reduction takes place. So oxidation must take place then at anode then. Okay, so at anode, this is our anode. Sorry, this is our cathode because reduction is taking place over here. You must correct me. And this is our anode because we can see oxidation taking place over here. So red cat, you must remember red cat. So at reduction takes place at cathode. Okay, so oxidation, this is our anode and this is our cathode. So I hope I was able to convey my point. Another thing I must tell you that is in our syllabus and we must discuss it, that there are two kinds of cell: electrolytic cell, electrolytic cells, and galvanic cell. They are also called voltaic cell, uh, of which we discussed an example over here. Daniel cell is the example of. So here we see that spontaneous here spontaneous reaction is creating electrical energy. Spontaneous reaction creating some electrical energy, as we saw it in the shape of what? In the shape of E naught of the cell. Okay. And here what happens is we did not discuss any example of this, but this happens when we use electrical energy to do some non-spontaneous reaction. Electrical energy is used to do some chemical work, chemical change, chemical reaction. So this was all the interplay of electricity and the the reaction that happens at the background for making some electricity or using the electricity to do some chemical work. Hope you enjoyed the lecture. I did enjoy it. Hope you did it too. Thank you for your time.